All right, so now we're going to take a look at the different types of numbers that we use in chemistry, uncertainty in the different types of measurements that we make, and then also significant figures. So the first thing we're going to take a look at are the two main types of numbers that we use. The first one that we're going to talk about are known as exact numbers, and these are numbers that have defined values. So for example, the relationships between different units within a measuring system, such as a 1 kilogram equals 1,000 grams, right? So there's exactly 1,000 grams in a kilogram. Those would be exact numbers. Let's say in a dozen, you have 12 of something, right? There's exactly 12 objects in a dozen. We also get exact numbers from counting. So you show up to class or to lab and there are 10 students there. Well, there's exactly 10 students, right? There's not 9.5 or 10.8. There are exactly 10 students in the class. So those are exact numbers that have defined values. And that's in contrast to inexact numbers, which typically we get by making measurements. So measurements of everything we talked about previously, length, mass, time, volume, etc. They will be inexact, and those numbers would actually be, those measurements would be dictated by our measuring device. Okay, and we'll talk a little bit about how we read different measuring devices here to report those numbers, those measurements. So when we're dealing with inexact numbers, we need to report that measurement so that we are able to indicate how certain or uncertain we are about that measurement. So that brings us to this whole idea of significant figures. So significant figures, which you often abbreviate as SF or just sig figs. Okay, these are the digits in a measurement that are meaningful. You can think of them as meaningful digits in a reported number. So every single measurement will have some degree of uncertainty associated with it. And this uncertainty is reflected in the last digit reported, which that last digit is always going to be estimated, which by default means that it's uncertain. And that uncertainty then, like we said before, would be dependent upon the measuring device that's used, and specifically the graduation marks on that measuring device. So the last digit of any measurement is going to be uncertain or estimated. So let's take a look at an example. If I have this particular thing, this looks like a SD card, for example, and if I use this top ruler to measure the, in that case, the width of the SD card, right, we line it up at the 0, assuming this is 0 over here on our centimeter ruler. So here, that's a 0. We have 1, 2, and then 3. So if we line up the edge of the thing, so right about here, okay, we know for a fact that this width or this length here, it's more than 2, but it's less than 3 centimeters. So we know that it is 2 point something centimeters, right? We know for a fact that it's more than 2, but less than 3. We're absolutely certain about that. What we're less certain about is how much between 2 and 3 it actually is. So somebody looking at it may think that it's 2.4. Somebody else may think that it's 2.5 centimeters, right? Because they think it's exactly in the middle. Well, guess what? These two here, these are estimated, right? We're not 100% certain about how much between 2 and 3 it actually is. So that's your estimated digit, that's your uncertain digit in that measurement. And the way that we represent that uncertainty is with this plus or minus thing. So we can say, we can read, using this particular ruler, we can read lengths or widths, for example, to plus or minus the 10th place, so 0.1 centimeters, right? That's the first place after the decimal point, right? Somebody thinks it's 2.4, somebody else thinks it's 2.5 centimeters. If we use a slightly different ruler that has closer or smaller graduations, we can be a little bit more careful with how we make that measurement. So if we zoom in here, we can actually see now, there's our 0. And now we line up the edge of it again, and we're right about here. Okay, so again, we know that it's more than 2, less than 3, but now we have these even smaller guidelines or graduation lines to use. So how much does each of these smaller graduations actually mean? Well, there are 10 of them, so each of them would be 1/10. So this is 2.1, that's 2.2, 2.3, 2.4, 2.5, 0.6, 0.7, 0.8, 0.9, and then 3. So we know now using this bottom ruler that the length here is more than 2.4, but it's less than 2.5, right? So it's between these two tick marks or graduation marks on this particular ruler. So we know for a fact that it's 2.4 something centimeters is our unit. So how much between 2.4 and 2.5 it is? Well, that's what you get to estimate as the person making this measurement. I think it's exactly in the middle, so I'm going to say it's 2.45 centimeters. Somebody else may think that it's a little bit past midway, and that's okay. They may think it's 2.46 centimeters, and that's fine. This is still showing that the last digit is uncertain. So the way that would represent this uncertainty is plus or minus now the 100th place, so 0.01 centimeters would be our uncertainty. So the smaller the graduation marks here, our uncertainty is also consequently a little bit smaller. So a little bit more sure about what that length, or in this case, it's the width of this object. So when it comes then to making measurements, we need to pay close attention to our measuring device. So whether it's a ruler, or for example, if it's something different, like maybe a graduated cylinder that looks something like this. Let's say that this is a graduated cylinder. We have our graduations on here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And just imagine that these are all evenly spaced. Okay, and let's say I put some water in here, and I see that the water is going to adopt this characteristic shape that looks like a smiley face or a half moon. That's known as the meniscus. And we always read the bottom of a meniscus when we're looking at water. So we get that at eye level, and then we read what it is. So we need to pay attention to what these smallest graduations are. So each line here represents 1, and this is milliliter. So we have 1 milliliter, 2, 3, 4, 5, 6, 7, 8, then that's 9, and then 10. So using this particular device, we can now say that this volume is more than 3, but it's less than 4 mils or milliliters. So we know that it is 3 point something milliliters, right? And we can estimate now how much between 3 and 4 it is. I think it's maybe about 7/10 of the way up. So that's my uncertainty, that last digit. So we can say plus or minus 10th place, or plus or minus 0.1 milliliter. Somebody else may think that it is 3.8 milliliters, and that's perfectly fine as well, because we are still reflecting the uncertainty in the measurement based on the actual graduation marks on our device. So when it comes to your measurements, we need to pay close attention to our significant figures, which are again the meaningful digits in a reported number, and there are rules for identifying significant figures. in a particular measurement, and the rules are, it's very easy to get confused with the rules, but they're actually really simple. Any digit that is not a zero is always going to be significant. So any non-zero digit in a number, in a measured number, is significant. So 112.1, all of these are non-zero digits, so this has 4 sig figs. The issues arise with zeros. Okay, zeros is where people tend to get tripped up a little bit. So let's first of all take a look at zeros that are between non-zero digits. Those are always significant. These are sometimes called confined zeros or sandwiched zeros. They're confined between non-zero digits, or they're sandwiched between non-zero digits, and those are always significant. So 305, obviously the 3 is significant, the 5 is significant. Now the 0 becomes significant as well. Similarly, 50.08, these two are between non-zero digits, so all of these are significant. If I had something like 102.001, well then the 1 significant, this 2 is significant, the 1 at the end is, and all of these zeros now are confined zeros. So this has a total of 1, 2, 3, 4, 5, 6 significant figures in it. When we have a decimal point in a number, the zeros at the end of that number are significant. Okay, so I'm going to jump down here. So if I have a number like 1.200, do we have a decimal point? Yes, there it is. So zeros at the end of a number with a decimal point are significant, right? So this one then would have the 1, the 2. Now the zeros at the end of the number with a decimal point, so all of these will be significant. If I had a number like 0.0, I'm sorry, let's say 1 point, or 100.0, okay? Do we have a decimal point in the number? Yes, there it is. So all the zeros at the end of this number will be significant. So the 1 is significant, this 0 is significant, that one's significant, and that one is significant as well. So this is going to have 4 significant figures. Now remember, what is this actually telling me? This is saying that when this person made this measurement, they were able to estimate to that last digit, right? They were able to say, well, it falls exactly on the line, so we can estimate it to the to be 0.0. Leading zeros are not significant. And leading zeros are just the numbers at the front. I'm sorry, the zeros at the front of a number. Where there are no non-zero digits ahead of it. So for example, 0.0023, these zeros at the front of this number are not significant. So just the 2 and the 3 are significant. Similarly, 0.00001, only the 1 is significant. These are considered leading zeros, and they are not significant. If your number has zeros in it and there aren't any decimal points in that number, then the zeros at the end are considered not significant. Your book says they're ambiguous, but to be unambiguous, we're going to treat them as being not significant. So we're going to say trailing zeros, which are zeros at the end, are not significant if there is not a decimal point. There isn't a decimal point in the number. So for example, if I had 150, okay, we consider the 1 significant, obviously, and the 5 significant. The 0 here is a trailing 0, no decimal point. We're going to say 2 significant figures. Similarly, if I have 1,000, okay, the 1 significant, 0s at the end, trailing zeros, no decimal point, 1 significant figure. Without any more information, that's as much as we can say. To avoid any ambiguity, ideally what you want to do is to express your number using scientific notation to kind of get around that problem. But to make it simple, that's the rule that we're going to follow in our class. All right. So once we identify our sig figs, we then need to do our calculations. And just like there are rules for identifying significant figures, there are rules for working with sig figs in calculations. And the rules are different whether we do multiplication and division compared to addition and subtraction. And we'll take a look at some of these examples.